Hi, my name is Digvijay, and in this lecture, we will talk about the importance of modeling resolution in energy system analysis. The main learning objectives of this lecture are to understand the importance of modeling of energy conversion technologies and evaluate the impact of different models on power system analysis. The same will be explained through examples on impact of modeling on power to gas electrolyzers and power to heat pumps. Technical analysis plays an important role in evaluating adoption of a technology, based on which economic evaluations and decisions are made. Errors from incorrect or overly simplified models can lead to incorrect conclusions about the technology. Therefore, attention must be paid to the models and insights included in the analysis. We will start our discussion with power to gas electrolyzers. In power system analysis, studies evaluating the role of electrolyzers as resources to support the grid frequency, little to no attention is given on effect of constant modulation of power input to the electrolyzer on the electrolyzer system itself. The electrolyzer is made up of smaller cells that conduct the electrolysis process. To measure the health of electrolyzer, voltage, current, or VI curves of the electrolyzer cells are analyzed before and after an operation to judge the impact on its health. Let us consider a detailed and a simplified model of the electrolyzer to showcase the importance of detailed models. The detailed model includes equations concerning mass flow rates, thermal and electrical dynamics, wear and tear, etc. This model allows us to extract voltage and current information of individual cells. On the other hand, a simplified model, typically used in power system studies, called the constant power load model, contains none of this information. VI plots cannot be obtained from this model, and it assumes that the electrolyzer will accept any power set point provided to it. Now consider this scenario. Operator of a wind power generator creates a schedule of its power generation for the next day and submits it to the grid operator. However, the schedule provided by the wind power operator is still an estimate since wind is unpredictable. To adhere to the promised schedule, it asks the electrolyzer for help. Under this agreement, the electrolyzer absorbs excess power in case of overgeneration and will reduce its power consumption in case of undergeneration. This flexible operation of the electrolyzer would help the wind generator to stick to its schedule. Let us see how this planned variable operation impacts the electrolyzer using the detailed electrolysis model just discussed before. The detailed model is provided with this variable power input for an entire day. At the end of the day, the VI plot of the cells is extracted and compared with one before starting the experiment. Both exactly overlap, indicating that the electrolyzer is in perfect health even after a highly variable operation throughout the day. Now let us extend this to 1 year. On comparison, the VI plot of variable electrolyzer operation for 1 year with the original one, it is observed that the VI curve has shifted. What does this mean though? This means that the cells have degraded over time, resulting in lowering of efficiency of the cell. The detailed models help in evaluating this decline. In this case, the decrease in efficiency is 0.8%, which for a 5-year variable operation period would result in almost 4% decrease of efficiency. Such information cannot be obtained from simplistic models, and we must use more detailed models. Next, let us look at electric heat pumps. Heat pumps are energy conversion devices that use electrical energy to transfer heat from a cold place to a warm place. It may seem counterintuitive to thermodynamic principles when I say that heat pumps push energy from a cold place to a warmer place. So let me try to give you a better picture. This figure illustrates the operation of heat pump. Let us say outside temperature is 2 degrees. A liquid refrigerant such as R410A goes around in a loop, changing its temperature when the conditions change. Now, let us start at the evaporator. The liquid at point 1 is cold, almost 0 degrees, when it enters the evaporator. Heat flows from the outside environment to this liquid, raising its temperature. The electrically powered compressor increases the pressure and thus the temperature of this liquid. Therefore, at point 2, the liquid refrigerant is now extremely hot. This is where it enters the room and transfers heat energy to the room. The liquid then flows through a valve that relieves the pressure and returns it to a low temperature, and the cycle continues. Unlike devices such as electric boilers or electric arc furnaces, where electrical energy is used to generate heat, heat pumps operate by using electrical energy to transfer heat. So, to measure the effectiveness of heat pump, we use a metric known as coefficient of performance, or COP. COP measures how effectively heat pumps can transfer heat from a cold source to a warm sink. Mathematically, it is represented as a ratio of thermal power to electrical power, Q over W. This can be used to calculate the electrical power consumption of the heat pump given a thermal demand. COP is a property of the heat pump that is also dependent on temperature difference between the source and the sink. It has been shown in multiple studies that COP can be modeled using this quadratic equation. Here, delta T is the required temperature difference between source, such as ambient air, and the sink, such as domestic hot water. Let me show you the impact of detailed COP model versus the constant COP model, which in calculations for electrical power consumption. Consider the first day of January in San Francisco. The ambient air temperature for each hour of the day is shown in red, while the hot water requirement is constant at 55 degrees, shown in black. When we use this equation, the COP is calculated as shown by red line in the figure, while a constant COP of 3, shown in black, is assumed, which is how heat pumps are usually modeled in energy system analysis. Let us assume that the thermal power demand is fixed at 100 kilowatts. So, the electrical power required to produce 100 kilowatt of thermal power is obtained by dividing 100 kilowatt by the COP. Using a simple model, the power consumption is constant at 33.3 kilowatts, shown in black, whereas using the variable COP model, the power consumption is variable, shown here in the red line. To add a little more context, suppose 100 such heat pumps are being analyzed for power consumption and economic analysis in the Netherlands. Also, let us assume that the weather conditions are same in San Francisco and the Netherlands for this particular day. So the COP dependence on temperature is same in San Francisco and the Netherlands. The electricity price in the Netherlands during the day is shown. Using the power and cost curves, we can calculate total electricity costs for heat pump operation for the day. Using a simplistic model, the costs come to about 78,000 euros compared to 69,000 euros when using detailed models. That is quite a lot of money, wouldn't you agree? Hence, detailed models are preferred over simple models for this kind of study. To recap, in this lecture, we learned about the importance of model detail in energy conversion technologies for simulation-based analysis. We specifically looked at electrolyzer systems and heat pumps. We arrived at the conclusion that appropriate consideration must be given to the type of model used for an analysis. When using simplistic models, consideration must be given to insights obtained from the models. Thank you and see you next time.